In this next example, we'll be talking about how to pick a value for a that's going to be a portion of the function that allows the overall function to be continuous. But recall the change in this function doesn't actually change the process in which we approach it. Step 1, we need to make sure that the function value exists at a very specific point. In this case, if I'm looking at the value of 3, again, that's where the breaking point is. This is continuous everywhere on its domain. This function is a linear function, and therefore will be continuous everywhere on its domain. We just need to know what a is so that these two functions will approach the same value at the breaking point between those two functions, which is 3. So my first step is going ahead and just simply plugging in 3 to the function. If I plug in 3 to the function, that means I'm plugging in 3 to this side. If I plug in 3 for x, not a, for x, that's going to give me 2 times a times 3, giving me 6a. So this is what the function value is supposed to be equal to. The next step is taking the limit as x approaches 3 of that function. The problem, however, is that as we approach the x value of 3, we have to be either on this function or on this function. So we're going to have to look at each function separately. So I'll work from the left first, giving me the limit as x approaches 3 from the left of x squared minus 1. If I attempt to plug in 3 to this limit, I can plug in 3, giving me the limit value of 9 minus 1, which is 8. So again, from the left, as I get closer and closer to the x value of 3, this function is getting closer and closer to 8. Now, I'm going to write this down, although it's not something we actually need to look at. We don't need to look at it because the limit as x approaches 3 from the right side is actually just working on the function that we already plugged x into. And this is just going to simply give me 6a again. So now I need the function value to be equal to the limit value, and for these two pieces to be equal, I need 6a to be equal to 8. Or in other words, I need a to be equal to 4 over 3, because I'm going to take 6, I'm going to divide both sides, and that's going to give me 4 over 3. So this a value will allow the function f of 3 to be equal to this sided limit already, and therefore equal to this sided limit, and then these two limits will also end up being equal. This is the value we were looking for to plug in for a in order to make sure that this function was continuous everywhere. The same rules will be applied for this problem, such that the only difference is that we're approaching the value of 3 on this function from both sides. So when I take the limit as x approaches 3 overall, I'm simply approaching as x approaches 3 on the whole function, because I need simply to be able to plug in 3 for this and get back b. Well, if I plug in 3 for x, there's no x's in this side of the function to take anything in. So basically, whatever this limit equals to is what my b value needs to be equal to, because f of 3 is simply equal to b. There's no x's to replace, so I'm getting back just the value b. When I simplify this, it's going to be the limit as x approaches 3 of x plus 3, mainly because I'm going to factor this into x plus 3, x minus 3, and the x minus 3 on top and on bottom will cancel. When I plug in 3, I'm going to get 6, and therefore the limit must be equal to the function value, so b must be equal to 6.